One thing I need to do for the compiler, I'm not going to be able to stream a lot next week, which means we're basically at the point where I'm going to have to stop for the holidays. What I want to do is I want to write, I might do it during the holidays. I need to do the roadmap for what's left because we're getting extremely close to being able to actually run the full pipeline of the compiler. And there's a few more things I have to clean first. This to do is already becoming obsolete. So I think I will want to start writing a roadmap for the rest of the project. One thing I wanted to do next was as part of the code generation. If I go back to the lowering, I think I want to make a change to the algorithm that is described in this research paper I've been using for the IR generation. I have already made a change, which is I'm using block arguments instead of using phi variables. But another thing I want to do, I think, is in resolve name. Here, I think I want to change this function to always put an argument to a block, regardless of whether the value was found in the block or not. Well, not exactly. I want to change this case. I want to always make a block argument regardless of the parents, I think. Let me explain. Here's me compiling with the current pipeline this function here. Well, those two functions here, this module here. It generates a bunch of things. If I go watch this is the parsed version of the code. This is the validated version of the AST. So we can check that the linker will think that indeed this call to foo here points to this particular foo here. Like that's the current version of what has been compiled. And here in the terminal is the generated IR for those functions, which is aiming to be close to the LLVM1. And if we look at the function bar, for instance, there is just a while loop there. It has a bunch of labels, so the function starts at label 0. We are assigning registers, and every block finishes with a jump or a branch or a return or something like this. And I use block arguments since this is a single static single assignment. I never remember if it's static single assignment. Yes. And that means that a register is never assigned more than once, which means for something like the x value here in the loop that changes over time, the label that corresponds to the while condition, which is this one, which compares something with 0, which is here, receives an argument which is a what register are we? Well, give me a value of the register. This register I1 will be provided by the jump or branch instructions to know what X is, basically. And what I want to change, I think, because here, when we jump from the beginning of the function, we are using I0, this 0 value, because at first X equals 0, so this while loop will never happen, basically. And what else did I want to do? Yes, when we jump back from the body of the loop, which would be label 4 here, we are giving another argument, which is this I10 register, which is the result of subtracting I1, of subtracting I1, which is the one that we started the loop with I9, which happens to just be 1. Now, one thing I want to change, I think, here, the labels that have only one parent, they don't need to declare an argument because the register can be traced. But I think I want to actually keep track of the registers because this will help me a lot with register allocation. If I know always what shape the stack must be in from one label to the next. So here, I think for this purpose, I'm gonna change this piece of code to always be this, basically. If I try that, one thing I haven't given a single thought about yet is the optimization phase, which should be on the IR. We're not there yet. Okay, so here, if we look back at this function, so labeled 0 is a type of a function. We're assigning, actually, if I just do this, it's all visible on screen. Okay. So 0 is label 0 is start of the function. We're creating a register I0. We're giving the value 0, which is our x. We're giving this argument to jump to label 1, which is the condition of our while. Here we're doing an assignment of 0 to I2. We compare I1 to I2. We store the result in the Boolean 3 register. We branch based on that register. If it's true, we jump to label 2, which is the beginning of the loop body. Otherwise, we jump to label 3, which is the end of the function here with the return. And now we are giving I1 as an argument to the label 2, which has I4 as an argument. So we know, okay, and that should help us know exactly what shape the stack needs to be in when we jump from one function to the next. Because whatever happens in this, the outcome of the stack must be this, basically. So when we do register allocation when doing the code generation, this will be very useful to know. We start with... that's wrong. That's wrong. That's good to know that's broken. Okay. That's good to... Oh, wait, no, it's not broken. Is it? Wait. Because here I'm giving I4 in this branch, despite the fact that label 2, which is the body of our while, starts with I4 as an argument. So what do we do here? We assign 2 to I5, okay. We do a modulo between I4, which is X, and I5, and I store the result in I6, okay. I7 contains 1. We do a compare for equality between I6 and I7. We store the result in the Boolean B8, which is the if here. Oh, so if this is true, we jump to label 5 with X that has not been modified in any way. So it is indeed correct that at this point, this is this value here that we want to jump with. And otherwise, we want to jump to label 4, which is this one, which is the body of this if with I4, from which we jump with I13, which is the argument, which will be X minus 1. And we jump back to the loop condition. Okay, yeah, that makes sense. I think that's correct. So now I need to think about what I want to do next. One project I want to tackle at some point is I want to do an export of this IR into the LLVM IR because, it will be very nice to be able to actually try to use the LLVM backend and see if what we have generated actually compiles to an actual program. That would be good. That's one thing I want to do. I want to do probably another pretty printer for to add another layer to this, which will be what the IR looks like. I want to do an optimization phase on the IR. And I want to do some cleanups. I desperately need to do a stream, like a week of comments and cleanups, because after the big refactor that took like a month and a half, the code is not in a state I'm happy with. Like contrast, for instance, the documentation on if I were to go to the stages parsing monad, like look at the amount of comments here. Like most functions have at least a line of comments, and there is a big module comment. If I go back to my lowering monad, there is not a single comment in this. So I really want, with the cleanups, with the refactor, things are in a better state than they used to be. But I still want, I think, to spend like a week to just to do cleanups. There's one cleanup I wanted to do. Fix dir has been done. I want to remove the type base name from the type parameters. Let's do that. Let me just quickly... Oh, I didn't commit this before. Okay. So that was a bug that we fixed the other day. I'm gonna commit that on its own first. Okay. Oh, and I still haven't moved from the... Yeah, there's so much cleanups I have to do. We'll see how much I can do next week before I go on vacation. This is fix block seal. Oh, fix blocks not registering temp arguments. And now make every register a block argument. With that done, let's try to do this change here, because that's a thing I have from pre-refactor of the analysis phase that I think is completely obsolete and ugly for no reason. So let's change it. If I go to validated here, in this file, a type that is parameterized is a type in which at any point I could have, instead of an actual type, a type parameter, which is like the type parameter of a struct or a function or something like this. And when I do this, I have always the base name of the type from which that parameter comes from. I think nowadays, with the proper separation between name resolving and type checking, this is no longer required. Changing this will break everything, but it will result in a lot of code becoming a lot cleaner. So let's see what breaks. Indeed, this is not a hash map of base name identifier. This is purely a hash map of identifier. Let me just recompile. Okay, so there's probably a few places here where I return. So I traverse with go, okay. And here I return left base name and the thing. I don't need that. I just did need the parameter name. That means type parameter in resolved can be changed to remove the base name here. Do I need to remove that? It's probably not a bad idea to actually keep it there, even though it's no longer required here. Tempted to instead just put that on a new line. And this zoom level I'm usually working at for this project on stream, this is a tiny bit more readable. Okay. What do we have next? Here. So I'm giving the base name, which is probably fine. But however, validate type alias type. Here, okay, so let's have a look here at all the places where I have a hash map with the base name. Because I believe this is no longer required. It should be just the identifier. Okay. So here this map base name goes away. Lookup base name goes away. This is just an identifier and no longer the base name. Which means here... Oh, did I already fix that? Okay. Interesting. So lookup parameter has still a... there we go. That's just an identifier now. Verify type here. That's because that's just an identifier. Let's have a quick look here again. Do I have... Yep, a few more. Here, I don't need to zip with the base name anymore. I remember thinking about this while doing the refactor, but wanting to wait until the refactor compiled, because otherwise trying to fix this while also changing everything would have been a nightmare. Now that we're basically at a point where I need to do the roadmap going forward and I'm about to leave for the holidays, I can do this quickly, I think. Here I have somewhere a base name again. I don't know where actually. Lookup only of the parameter name. The logic behind this is from before I had the refactor, I was doing some partial type checking on generic functions before instantiation. And so I needed to be able to say, oh, this type T there is not just any type T, it's a type T that comes from this particular thing. For instance, if my function had a type parameter T and was instantiating a struct that has a type parameter T, but with int as the instantiation, I needed to be able to differentiate the T of the struct from the T of the function, hence using the base name. Now that I never do any type checking before before the function is actually instantiated, there is never a case where I need to do validation on a partial type. Therefore, I don't think this distinction is still required. Which is why I am going through this and removing all of the base names from places where they don't need to be. And here I'm returning a base name with the identifier. I can remove that again. Here I'm doing a zip of, and this goes away. The base name here goes away. I'll have to be careful and pay attention to the warnings. There's a bunch of places where we might be able to remove function arguments as well, which would be nice. Okay. We're at the point when the pretty printing is now what we have to fix, which is good. Just going to check something, which is going to force a recompile of this file and type. I just want to make sure that there is no warning. I didn't. Okay. So that means it should be fine. Now, let's try again to test 4. So what I will want to do here is try to introduce as many complicated template things as possible to try to see that we still resolve them properly. So let's introduce a struct A that's going to have 3 arguments, T, U, V. It's going to have 3 field, A1 of type T, A2 of type U, or let's do something more complicated even. Let's say that this is a B of T, U, V, and this is a C of T, U, V, and A3 is a D of T, U, V. What are those? Let's say that B is a simple type alias with 3 things, which I'm going to name differently just for additional confusion. And this is just an alias to the first one. Hello everyone, I am no longer doing the advent of code, I'm done for today, so I'm back to my regular project, my compiler. And here, let's rotate them again. This is gonna be EU again, let's say, and let's say that D is also a struct. With 3 arguments again. I'm basically trying to introduce as many... Hello! I'm trying to introduce as many type arguments with the same names used differently. Well, I mean, the whole idea behind starting to make a compiler for Pete was to be able to make some advent of code solutions in Pete. That was kind of the idea. In this, it's the same reason I have my basic brainfuck compiler, the BFS thing, which is to make it easier to write brainfuck stuff, to write my brainfuck solutions for the advent of code. But yeah, the advent of code was fun. Today it was a somewhat simple graph problem. The fun part has been to generate a actual dot graph of the graph input. This actually took longer than actually solving the problem because I wanted to use my own library for this, which is GraphWiz. Where are you? This one, which is on Hackage. And it turns out that one of my dependencies has been updated, and as a result, my library is now broken with recent version of GHC that use a newer version of the dependency. So I had to fix my library to be able to regenerate this to fix the advent of code. But yeah, I'm gonna need to publish a new version of my library, basically. It's only compatible with older versions at this point, which is fine. But yeah, that was today, and yeah, I have some amounts. I haven't done a lot of in brainfuck this year, but I have done the other day. I'm on the correct thing. I have done... if I look at the brainfuck, I think I've only done day 1 and day 7. But yeah, that's day 7, part 1 in Brainfuck. I did 2 days ago. I missed my stream because I was busy doing this instead of actually streaming in Haskell. I wrote, if that's interesting, I wrote on Reddit a explanation of how this works on the Advent of Code subreddit. Somewhere in there. Yeah, this one. So if that's interesting, you can have a look. This is an explanation of like how the brainfuck code is written. Yeah, no, the Advent of Code was fun. And so as a result, I'm back to my compiler project. I've just made a small change in the way I resolve template type arguments, and I'm now writing a manual test case where I'm just trying to see, and this is gonna just be D1 is gonna be just T, and it's gonna be fine. I just want to check when I have a complicated like set of like types like this, are they resolved properly? Yeah, that is exactly that. Only brainfuck characters are used by any of the brainfuck interpreters. Therefore, I can just write this, and that's purely a comment. And there's one exception. It is very standard for debuggers to recognize the hash sign as a print the state of the memory at this point instruction, but compilers will usually ignore it. And I make use of that in my little compiler that I haven't used for this version, but I've used for like previous days. Do I have a version? If I look at yes, my compiler that like generates brainfuck for me based on like brainfuck with macros basically will use that to indicate the shape. So the main function contains this and then calls the step function, and then this is an if block with the condition is this and the then is this. Like I'm using the fact that non-brainfuck characters are comments so that the output of my compiler contains like the name of the function and has like the structure like this. Okay, so test parameters will be a function with the same 3 arguments again. That will be returning of A, and I'm gonna give them in a completely different order, V, U, T. And this is gonna be purely return A. So I'm gonna have to take 3 arguments here. Let's take X, which is gonna be a T. Sure. My usual stream times are like on Tuesday and Thursdays from 8 p.m. Dublin time onwards, except, you know, with the advent of code and the vacation coming up, this is going to be very different. But yeah, that's the plan usually. And back in January, with the advent of code done, I'll resume working only in this compiler. The goal is to take a Rust-like language like this and to output another esoteric language, Piètre, in which the source code is an image. Because it's fun. And I am at the point at this point, lexing is done, parsing is done, most of the analysis is done, so like name checking, type checking, and so on. Lowering into IR, that's done. We have an IR of the functions. I will do an export to the LLVM IR at some point. That's not done yet. Code generation is not done, but the output, the bytecode that we will generate is done, and the assembly linking is done. So this image there was generated by the backend of our compiler, and all of the front end is done. I'm only missing the linking the two, basically, at this point, and a lot of other small things around it. So let me just finish writing this test. So if I have a X, okay, so I have those things. When I create an A value here, what is A1 going to be? It's a B of T U V where B is the first one, so it is the T, so it's going to be the V, so it's going to be Z. A2 is a C, which returns the third argument, which is the V, which is the third argument here, which is a T, which means it's X. And A3 will be this, which is a struct with a field D1 of type T, which is the first argument T, which is the first argument T, which is the value of type V, which is our Z value. So we never use our Y value here. Okay. So that should, if this is correct, then this should compile. And let's do a thing where to force an instantiation, here, let's call test parameters with 3 different types. And we're going to also test the type inference. So the first argument will be an int, the second will be a character, and the third will be a Boolean. Let's run that, and it fails. So maybe I was wrong about the required... Wait, no, this is an actual, this is not a bug, this is a diagnostic. What did we get? Struct ambiguous type. Oh yeah, that's correct. That is correct. So this is my compiler telling me that here I construct a value of type D, which is a struct, that has 3 type arguments, but here I only provide a value here of type T, and therefore the compiler cannot infer the types of V and U based on this. So here I could say, no need to give the first argument, it will be inferred from this, and I could say that those happen to be V and U, I suppose, for additional complexity. Okay. There is a, and here this will be with this syntax, I think. Error struct incompatible types. Okay. On line 18. That's this one. Oh yes, here I am saying that this is a DTUV for the order in which we're doing this, which means it's a VUT here. So here I said a few things here, and the compiler was like, well, that's incorrect compared to this definition here. So far, I'm wrong, the compiler is right, I'll take it. That compiled. And so we can check now. If we look at the version that has been instantiated, where is it? There it is. This returns a main A with Boolean character int. That's correct. And it did check correctly, so it did resolve things properly. And it did resolve that the type of A1 is T, the type of A2 is V. And this is... So this D1 is indeed... Okay, so that seems to have worked. Perfect. That means that my change that I've done this evening is correct, in the sense that we no longer need, since we no longer do any type checking on generic functions before they are instantiated, we no longer need to keep track of like, hey, this T is the one from the struct D, this one is from the type alias C. Things are being replaced properly. In fact, I'm very tempted to do a thing where I add one other layer here. This is gonna be VTU. This should compile the same. It does. The result is the same, so that works perfectly fine. That's great. Okay. And this is linked properly because here test parameters with int boolean character, the linker knows that this is this version of the function. Perfect. Perfect. What in... Oh, this is the function call in the IR for the foo function. And it calls, this is very verbose. Oh, because it's all of the type arguments. Yes, of course. This is the function test parameters where the type arguments are the built-in int, the built-in character, and the built-in boolean. Yeah, that's correct. Okay. So that is a change we can commit. Let me just reread through that change quickly. That looks good. Okay. I could probably go one step further, and I could remove it from, not here, validated, from resolved. Here, when I resolve the name of something in my program, for instance, when I encounter, I look at this function foo here, and there's an x here. What is this x? After the name resolving phase, it is going to be one of those. I'm going to resolve it to being a built-in type, a built-in function, a struct, an enum, a constant, a function, a type alias, a type parameter, a placeholder, a function argument, or a let variable. Nothing else. That's all it can be. I am tempted to say that I don't need to store the type parameter, the base name there at this phase. Because it will always be in the context of like, now I know I don't need this. However, it might not be a bad idea to keep it, just because if I do a pretty printing of this form of the AST, then it will not necessarily be resolved properly at that point. And like for debugging purposes, I think keeping it here makes sense. So I think I'm gonna keep it for now at this phase. Okay, let's try to start writing a very, very rough version of the problem. Is like, even if we do code generation this evening, I don't have any built-in function, which means a program that we generate would not be able to actually print anything. It would just be an image that looks nice that we could not even test. So I definitely need to work on having built-in functions and being able to link them. Well, I guess we could try to make some progress on this for like an hour-ish, and then I'll have to stop. So this would be, I don't have a folder yet for the code generation. So far, I have folder for the assembly, for the analysis, for, oh no, generation, there you are. Okay, I have nothing yet. So what are we going to need to generate, what is this going to be? Our input is gonna be the IR, which is this, where we have a function that has a label and then a bunch of labels and blocks which contain instructions and then a jump of some kind, and the instructions are not jumps. And we are gonna want as IR. So we are gonna want to get a function like this, and we are gonna want to output a sequence of instructions, and those come from the bytecode. Which is here. And the bytecode is a very simple thing. Oh, linker phase is incorrect. This is gonna be an unresolved instruction. The difference being, when I generate a function, I haven't done the linking yet, so I don't know the address of the other functions in the program. So instead, I store a name, a unique name that uniquely identifies a thing I'm gonna be linking against, and I then have the linking phase where I transform this to actually be every push of an address becomes pushing a int, which is the one we have resolved at linking time. So that's what happens during the linking phase. However, this is, I think, identifier is no longer correct. I guess I have text here. What I've been using so far as a unique thing is the name. Is this thing that has a module name, identifier, and the name on the list of the names that are the type arguments if required. However, this is not exactly what I need for this, because I'm going to need also, each function will have a unique name, but it will also have a unique address within the function, which is the block label, basically. Because we can jump directly to a label. We are using the same jump mechanism through the image for jump within a function or go to or jump to a function. So I think this is text is not accurate. I think this is going to be a combo of name and int, which is already on its own going to break a bunch of things. But this is going to be what generate bytecode is. Although, of course, oh, wait, at that point, can errors happen? Can there be any error at this stage of the compiler? And by error, I mean user error. Can incorrect code from the user result in an error in this phase? I think the answer is no. If we have generated the IR at this point, this should be a total function. There should not be anything going wrong. If anything goes wrong, it's a bug in the compiler. Therefore, we don't need to, for this function to return anything in some kind of diagnostic monad so we can keep track of the diagnostics. I think at this point, we don't need to do that. So this will be purely doing, I'm just going to not do it yet because I've just changed the representation. So the linking phase and the assembly phase are going to be broken. Let's fix them first. So let's fix this. I'm going to need, that's the convention I've been using in this. I'm using third-party libraries, then my code, okay? So here, same thing. I need the name in scope. Which means here in the linker, I have somewhere a hash map. There we go. I'm actually just going might just introduce a type alias, I think. An address is a name and int. Which means here, this is a hash map from address to int. There we go. Let's see if I have other mentions of text. Initial state, it's going to be an address to int. So this should be a hash map from name. This is going to be the function. This is going to be this is going to be the instruction for a function, basically. Oh, here I'm using a list, interestingly. Okay. I should probably change that to a sequence. Although I guess I can just change for now my generation to just be a list. And we can fix that to a better container later. Famous last words. Okay. Aha, I'm doing some nice circular stuff where this function takes as an argument the final state that it also returns. That's neat. This code is old. Well, we'll see what breaks when I change this, I suppose. Yeah, let's see what breaks. So this thing expects some text and got. So why does it expect the registers to be? So should probably be an address there, I guess. Main will be the name of the main function. Aha, instruction is unclear. Here, this is the function that we take as input is the IR version. The instruction we emit in the output is a bytecode instruction. Okay. Does this compile? It does. Perfect. Okay. So I can, I guess, start by committing this small change. Use symbol name in linker assembler. Okay, so now how do we generate instructions for a function? Do I have the guarantee actually as part of my lowering into AR? Because in the IR, my function has a bunch of blocks with a label, and I know which block is the starting block. Do I need that, or is it always going to be the first one? I suppose the collect block could do some shenanigans there. Because here I suspect the expectation in my linker is that the first block of every function I suspect the first block of a function will be the address I use for it. Entrance count, okay. I see. This one is the one I'm using incrementally. Okay. Okay. So when I do a function call, the entrance name. There we go. Okay. But that means that when I do a push address, I need to make an assumption about. Yes, so I will have to assume that label 0 is the first. Because when I do the link, I will not necessarily, when I do the code generation there, I'm going to have to generate, jump to this address, and this address will be whatever the function name is, and a label, and that's going to be labeled 0. So I have to make the assumption that label 0 will always be the first label of. But it doesn't matter in which order I actually put them in the instructions. Okay, that's fine. Do I have somewhere in the IR something that explicitly states lowering? Do I have something that says that the start block is always 0? Because that's something I will need to rely on, basically. I think I'm just going to remove it from the IR for now. Because this is something I can't check anyway, so I have to make this assumption. Okay. Next. This is gonna break my main, I think, possibly. No, it doesn't. Perfect. So, with that done, then I should be able to start writing code generation. Let's have at the top here, on one hand, the IR, on the other, the bytecode. And let's go. So this will be, it's a non-empty list, okay, of label and block. So making it a list is a bit annoying. That's fine. So I have a function as an argument that contains things, and this is gonna be a concat map of visit of the fun blocks. And fun blocks, I guess I could here do a not here. Visit is fine. Fun visit will be something that they could block as an argument. Well, it takes the label and the block, I suppose. So it's going to be the label and the block. And what do we do here? We are going to need an entrance. And the entrance is going to be an entrance instruction with the address being the name. Oh, I need the name of the function. And be the name of the function and its address, which in this case will be the label. Okay. And so this is going to be that, and at the end, the last instruction will be the terminator, I suppose. I really want to make this a sequence, just because inserting things at the end will be so much better with a sequence. So I am going to need qualified as sequence, which means I have a non-empty here as argument. So this is going to need to be in an E2 list. Well, this concatenate actually doesn't work. Because I'm going to get a list of sequences. That being said, sequences are monoids. So I think mconcat should work. So mconcat in the case of a sequence of int, let's say, would be this will be a function from list of sequence of int to sequence of int. And it does specify the constraint, but I think the constraint is valid. So if I do an mconcat of pure 3, pure 4 as a sequence of int, I get perfect. So here, well, can I do then a fold map? Yep, this would be a fold map, traverse to something that is a monoid, and then concatenate. So this is a fold map visit of the fun blocks, and I don't need to do any conversion to lists or anything like this. As long as this returns something that is a monoid, which a sequence is, it's going to be able to concatenate them together properly. Perfect. So now visit can return a sequence, and that's going to be just fine. And I want to do this as a sequence because this is always going to be... That's not going to be monadic, actually, I suppose. Because this is going to be... let me think for a second. Because this is going to be basically, I need to create the instruction for the entrance. I need to create the instructions for the actual instructions within the block. And I need to create a special instruction for the terminator. So this is going to be make entrance. I guess I could just actually keep of the label and the block, and I'm going to need both. And this is going to give me one instruction. Maybe it's going to give me actually multiple. So let's do just a mconcat, I suppose, there again. This is the make entrance. This is the... I might need a state for this, but we'll try to see. Generate block code of the block, and or make entrance, make block, make body, and make terminator. And now we just have to define what those functions are. Make the entrance is going to be the easy one, because make the entrance will just be I have the label, I have And I don't need the block, actually, I believe. So making the entrance is just returning an entrance instruction with an address that is the name of the function and the label. And that's it. Making the terminator is going to be complicated, but let's try to do it. I can't do that. I can't do the terminator on its own. It needs to be done at the end of the instructions because I need to know what the shape of the stack is, because if it is a return, I need to unstack everything, basically. I need to unstack everything. And to know what needs to be unstacked, I need to know what is on the stack at that point. Therefore, I can't do this on its own. So this is purely going to be make entrance label with the label at the beginning. And I think that's the operator for sequence. At the beginning of a series of instructions. And this is going to be generate block code with the block, which is going to be a completely dedicated function. Okay. This will take this will need the name of the function still, because for local jumps we will need to know the name. And this will take a block from the IR and return a sequence of instruction unresolved. Now, is this just a matter of doing a fold over the instructions to get the shape of the stack? I want actually to see, let's see if there is, or if I should just use a statement out for this. Is there a fold that also gives me, that transforms a structure but gives me the accumulator? I'm thinking of a traverse with a writer monad, basically, I think. But this would be something along the lines of I have a function from an accumulator and a value to the new accumulator and a new value, and I have a traversable thing of B, and I return A, the last accumulator, and a transform version of the thing of C. No, that doesn't seem to exist. Okay. Oh, this would also need the first accumulator. That may be why. There we go. That exists. Given some state S and a value A, and a function that returns the new state S and a value B, a starting status S, a traversable thing of A, give me the final status S and the translated version B. That's pretty good. That's basically what we want. That is basically what we want, I think. It's kind of the equivalent of running a state monad manually, I suppose. Because what we are going to want to do is is gonna be this map with an accumulator left. Yep, that's the one. Where we are going to use a step function that we haven't defined yet. Our start accumulator will be the state of the registers, so the two registers there at first. So this is the block arguments. And I am iterating over the block instructions. That gives me the stack at the end and the instructions. And with that, I can return a sequence from list of the instructions and an additional instruction at the end, an additional series of instructions at the end, which is going to be generate the terminator using the stack at the end of the block and the block terminator. Okay. Our step function is going to be a function that's given a stack shape, which is going to be the list of registers on top of the stack. And an instruction will return, an instruction as defined by the IR will return this is actually going to be again a mconcat actually, because I'm going to be returning a sequence of instruction at every level. Return the corresponding instruction and the new shape of the stack afterwards. Okay. So we're stepping and we find one of those instructions. What do we do? I might not support all of them at first, but let's try to have a look. I have an add. That's the target register. And that's register 1, register 2. I'll have to think about the ordering as well. I need to make sure that the proper register is on top of the stack for things where the order matter, like a divide, for instance. So this is going to be, I need to check, I need to get, this is going to be complicated. This is going to be, I need to make sure that those two registers are on top of the stack. Oh, I don't know if a register is used more than once. I am going to need to do, okay, I can't do that yet. I'm going to have to do a phase of register allocation first, because there's a big difference between this value can be destroyed versus no, it cannot. And I don't know that at this point, because the stack will be destroyed when I do an add in Piètre will combine the two top level values of the stack together, thereby destroying the values, which means I need to do register allocation so that I can check whether I still need the value or not. And it's made even worse by the fact that I will need to keep track of which registers are actually references. Huh. Okay, I'll have to think about this a bit more, and I will probably do that off stream over the holidays, because I can't just jump into this without being prepared. There's so much I need to figure out before I do it. I don't think I'm gonna actually make enough progress this evening on this without a proper plan. So let's stop this for the evening. I still think this is more or less the correct shape of the code, but the details will have to be figured out. And yeah, I think I'm gonna have to do, I cannot just be like, because my plan was, if I look at the shape of the labels, I know that like, oh, when I do this block, I enter with the stack only containing beyond stuff like the return address of the function contains the register I1 on top of the stack. And at the end of this, I do a branch and with B3, and I know that my stack contains I1, I2, B3, and I want to only contain I1 when I jump to this, basically. So I know that I can pop B3 after I'm done with the branch. I can pop the I2 after it's done, but I need to be very careful because there are cases such as here where I4 is an argument that is used in a modulo, therefore consumed, and I still return the value of I4 here, which means that this modulo cannot erase I4 and will have to duplicate it before. Which means I will need to do register allocation and decide, okay, given the shape of my stack here, given the operations I'm doing, and given what the shape of the stack is in the output, what values of the stack can I destroy and what values can I not? And I might also need to change the shape of the IR because here I think when I have like function with arguments, they are just given here as first values. Like this is what the stack looks like when calling the first label of the function. However, I do have a notion of reference in the language, which means when this function returns, the value that was stored in this part of the stack will need to reflect the modifications made to it. Therefore, it cannot be consumed by other operations. And at this point in the IR, this is lost information. So I am going to need to rethink how I do this. I'm going to need to rethink this. I'm going to need to do register allocation. I'm going to need to keep track of how a function returns something. Although I suspect I could change my return statement to also always contain the values of the, like a return needs to contain the values of the um, references arguments, and therefore I could do a lookup of like, okay, what values are they by that point, and that will give me the registers, and that would allow me to keep track of what needs to be returned. Yeah, I might do that. This might be something I can do, which would mean changing here in the IR a return terminator might not just be a maybe register for the value, but also a list of register, which is the ones that happen to be required because the function actually returns like references. But that would still not fix the fact that I need to then do some analysis of where each register is used so I can then figure out which ones can be destroyed and which one cannot. I have no plan on how to do this yet because I didn't think that far ahead. So I'm not going to do that this evening. Let's make what I have compile. Even though it doesn't do much. Oh, I broke make entrance. Make entrance is just as we were saying, given a label. This one I could just make it directly. This is a bytecode instruction for entrance. using the name and the label. Which means I could even do a flip fold map of the fun blocks where there we go, a bit more concise. Function name. And that's also the function name. This is from list, I believe. Wait, where was it from? Yes, list. I need the name. And this is also going to return a sequence of unresolved instructions. And that is also going to be undefined for now. What is a label? In the IR, a label is just a label of int. Okay. So here I could use... Oh, do I have something like start label or something? I don't. Okay. But that means in the linker, I could use... Instead of using an int, I could be using the label, but that's fine. That's fine. I'm just gonna do for now a thing where I unpack the label here. Okay. Unused import, data sequence not used. Okay. Stack shape unused. Okay, and now this basic thing that does nothing. Remove start label from functions, from IR functions, always assuming 0. Prepare code generation. Okay. Well, there's so much I could be doing next. This goes away. But I haven't planned anything else, and I'm blocked on the code generation until I figure out those register allocation things. So I think I'm gonna stop for the evening. I will perhaps try to stream tomorrow. I'm not sure I'll be able to yet. If I can, I'll do the last day of the Advent of Code. And if I cannot stream tomorrow, I'll be back on Monday or Tuesday, which will be probably my last streams of the year, where I'll finish the advent of code and perhaps, if I have had time to think about some of the next steps for the compiler now that the big thing I was working on is done, maybe try to start working on this. Otherwise that'll be all for this year, and we'll start again in the new year with the roadmap. In the meantime, thank you for tuning in. This was fun, and I'll see you all next week, or tomorrow, perhaps, again.